Okay, 1.2 functions and function notation. So functions can take an input, so an x, perform operations on it, and then give an output, which is usually our y. In other words, we sub in x and we calculate the answer for y. Okay, so a lot of times you'll see a function look like a little machine here. So you put in x, you calculate it, and then the output is y. Okay. Function notation. So you might be wondering, well, it says f and x here. A little bit confused. So to represent a function f in terms of x, we denote the function with f at x. Okay. This is read one of two ways. The function at the value x or f at x. I'm going to refer to this as f at x. So for example, f at x equals 2x plus 1 is read exactly how I just read it, f at x equals 2x plus 1. Okay, for each of the following we're going to determine f at 2, f at negative a half, and then f at m plus 1. Okay, so if we have the function f at x equals 2x minus 4, we write this as f at 2 equals, now we can go ahead and sub in, because remember this is usually f at x. We sub in 2 for the x. Okay, so this is 4 minus 4, and we get 0. Okay, that one's an easy one. So now let's do f at negative 1/2. Okay, so let's sub in 2 negative 1/2 minus 4. We don't need a bracket there. Okay, so 2 times negative 1/2, I get negative 1 minus 4, and I get negative 5. Okay, the general form where we're given like an actual expression, this one's a little bit more complicated, but not too bad. So f at m plus 1 equals 2m plus 1 minus 4. Okay, what we're going to do is we're going to distribute that in. So we get 2m plus 2 minus 4, and we can collect like terms, 2m minus 2. Okay, next one. We're going to do f at 2 again. So we have 3, 2 squared, minus 2 plus 7. Okay, 2 squared is 4, so we get 12 minus 2 plus 7. That's 10 plus 7, I get 17. Now, f at negative 1/2, and I'm actually going to write it down here, just so I have a little bit more room. 3 times negative 1/2 squared minus negative 1/2 plus 7. Okay, negative 0.5 squared is 0.225, and then we multiply it by 3, so 0.75. Okay, negative negative gives us a positive, so we get 8.25. Okay, this one's a little bit longer. I might actually use up all this space. So what is f at m plus 1? Well, we need to sub in m plus 1, and we need to square that. Then we need to subtract m plus 1, keep that in brackets, and then plus 7. Okay, this is a little bit different. So don't just square the m and square the 1. Okay, as you remember from our review of polynomials, we have to rewrite this and we have to actually FOIL these. Okay, we can go ahead and distribute the negative sign into this bracket, so negative m minus 1. Now, let's do 2 at a time. So leave the 3 there and let's expand m plus 1, m plus 1. So we get m squared minus, or plus 2m plus 1. Minus m, we can collect these, make it a little bit shorter, plus 6. Now let's expand that m into the bracket. 3m squared plus 6m plus 3 minus m plus 6. And now let's just go ahead and collect like terms. We get 3m squared, 6m minus m, we get 5m, 3 plus 6, we get 9. Okay, C, f at x equals 87. So here's the thing, 87 is a constant. So this is actually, like, if you have the graph y equals 87, this is going to be a horizontal line through the number 87. Okay, so if we say what's f at 2, well, we're not actually subbing 2 in anywhere, so it's 87 no matter what. Okay, what is f at negative a half? And if you correspond to negative a half here, or 2 here, yes, it's also 87. Okay, and then f at m plus 1, it's going to be 87 as well, so it's going to stay as that constant. Okay, let's do it for this fraction. F at 2 equals 2 times 2 over 2 squared minus 3. So I get 4 over 4 minus 3, which is 1, so I get 4. Okay, f at negative a half equals 2 times negative a half all over negative a half squared minus 3. Okay, 2 times negative a half, I get negative 1. And then this, I get 0.25 minus 3, so I get like negative 2.25. Okay, so this is an actual fraction. Oh, I want to say 2.75. Yeah, it's negative, or positive 4 over 11. And sorry, this is 7.5. Okay, and then the same thing, f at m plus 1. We sub in 2 times m plus 1 all over m plus 1 squared minus 3. Okay, so we get 2m plus 2, because we expand that. Now, m plus 1 squared, we get m squared plus 2m plus 1 minus 3. So we can just collect those two like terms. I get 2m plus 2 all over m squared plus 2m. Let's go minus 2. Now there's something called mapping diagrams, and this is just another way to display maybe like ordered pairs, such as like x, y, and it's more visual. So a mapping diagram is a representation that can be used when a relation is given as a set of ordered pairs. In a mapping diagram, the domain values in one oval, okay, so like the first oval would be our x's or our domain, independent, and then the range would be in the second oval, which is like the y or the dependent values. Okay, and they're joined using arrows. Okay, a relation is a function if there's exactly one arrow leading from the value in the domain to the value in the range. All right, so let's do an example. Use the mapping diagrams to write the set of ordered pairs and then state whether the relation is a function. So 1 maps onto negative 5. 2 maps onto negative 1. 3 maps onto negative 5. 4 maps onto 0. 5 maps onto 0. 6 maps onto 5. And 7 maps onto 8. Okay? It doesn't matter if the y's repeat as long as the x's don't repeat. So therefore, yes, this is a function. Okay, let's list the ordered pairs here. 2 maps onto 1, 2 maps onto 2. So already, see how 2 points are coming from the 2 and mapping? Already, we know that this is not a function. Okay, 5 maps onto 3, 8 maps onto 7, 11 maps onto 5, 14 maps onto 4, and then 14 maps on 2. 6 as well. Okay, so it's not a function because of the 2's and because of the 14's. Okay, it wouldn't pass the vertical line test here. So every independent variable doesn't map to only one dependent variable. Okay, the 2 maps to 2 and the 14 maps to 2 as well. Okay, applications of function notation. So for the function h at t equals -3t plus 1 squared plus 5, what we're going to do is we're going to graph h at t and find the domain and range. So this is the exact same thing as if this was like a function at x, or like x and y. Okay, so we're going to sub the -2 into the t, and then the -1 into the t, and then the 0, and then the 1, and then the 2. So what we get for that is 2, 5, 2, -7, -22. So 2, 5, 2, -7, -22. Okay, and let's go ahead and graph. So -2, 2, -1, 5, 0, 2, 1, -7, and then the 2 is off the graph, which is okay. We don't have to graph all of them. Okay, we know that this is a quadratic because it's in the form y equals x squared. Okay, and then let's state the domain and range. So the domain of this one is going to be XER. Okay, so we can, for this equation, we can sub in anything for t and it will hold. I'm actually going to change this, TER. Okay, we have to be consistent with the variables that are used in the question. Now the range is in the form h. Okay, so HER such that, and remember h, what we're looking for here is like this maximum or minimum value, okay, which we have as 5. So all of the y values or the h values are going to be less than or equal to 5, okay, because it's opening down. Now B, this question wants us to find h at -7. Okay, so let's just go ahead and sub that in. -3, -7 plus 1 squared plus 5. Okay, so -3, -7 plus 1 is -6. When we square that, we get 36. And then plus 5. So we get -103. Okay, that gives us a coordinate, -7, -103. Example 5, given the graph f at x below, so the graph being obviously this thick line, and then curve, find the values of the following. So this is the exact same thing that we would do if we had an equation. We would sub in the -5. Well, we're just going to look at like the reference. So when we go to -5, what point references with it? Well, -3. When we go to -3, we get 1. Okay, and remember that's because -5, -3. Okay, when we get 0, when we're at 0, we get 3. When we're at 5, we get -2. And when we're at 6, well, the graph is undefined here. So we call that undefined. Okay, example 6. The temperature of the water at the surface of the lake is 22 degrees. When David scuba dives to the depths of the lake, he finds that the temperature decreases by 1.5 degrees Celsius for every 8 meters he descends. Okay, model the water temperature at any depth using function notation. So we can say the temperature at depth D equals, and this is obviously a line, okay, so plus 22 would be our y-intercept, and our slope would be -1.5 per 8 meters. Okay, and then we can call this temperature at D, and then this would be D. What is the water temperature at the depth of 40 meters. So the temperature at 40 equals negative 1.5 over 8. We sub in 40 and then add 22. Okay, so when we go ahead and do this, we get 14.5. Okay, so therefore the temperature is 14.5 degrees Celsius. And we want to use the units just in our therefore statement. Okay, and number 3, at the bottom of the lake, the temperature is 5.5. How deep is the lake? So we haven't actually seen this type of question yet. The 5.5 we'd actually sub into where the temperature is. Then we would be solving for D. Okay, so let's bring the 22 over 5.5 minus 22. Equals negative 1.5 D over 8. Okay, we get negative 16.5 equals negative 1.5 D over 8. Let's cross multiply up. We get negative 132 equals negative 1.5 D. Divide out the negative 1.5. And I get 88. Okay, so we can say, therefore, the lake is 88 meters deep.